So last time we went over just how the Fourier transform works, and the idea was the way we sort of broke into it is that you can think of a Fourier transform as if you have a real signal to Fourier transform that, you correlate it with sines and cosines. And so what we want to talk about today is just briefly talk about why this is a good thing, because you're essentially, and we'll come back to this later when we talk about accelerating scans, all the different frequencies are uncorrelated with each other, or orthogonal, another way of saying it. The dot product is zero. They're at right angles to each other, if you think of them like vectors. And so that's a powerful way to, there's other ways of doing this, but this is a powerful way to take something that has various kinds of correlations in it and sort of turn it into a bunch of independent pieces. So we'll talk about that. But we're talking about spatial frequency, and so the second part is to sort of transition to space, because I sort of described the first thing as an example. You have an audio signal, which is just a signal that varies over time, and how you decompose that into temporal frequencies. But we're going to be talking about spatial frequencies, which are variations in brightness that are like uniformly spaced bumps going across the image. So that's a spatial frequency as opposed to a temporal frequency. And then we'll talk a little bit about the cosine brain. Like, what if you had a really simple brain that just was a cosine? What does the Fourier transform of that look like? Because we're working up to what does 1 point in k-space look like? And because that's actually what gradients do. They essentially give you 1 point in k-space. And so what is that? That turns out to be a little hard to understand. So we'll come to that on Friday. Okay, so let's start back with quickly back with our picture of e to the minus I angle business. And if we look at that angle there, we can, and we have a length of that vector being 1, then we can decompose that into sines and cosines. And the opposite is basically the sine. That's the imaginary part. And then the adjacent angle is the cosine. That's the real part. So when we write down this e to the I angle, we can think of that as basically equal to a cosine plus a sine. So you'll often see it written out this way. They don't put sort of the x unit vector in there, so they just say cosine of phi plus I, sort of a bold I, times sine of phi. So I remember looking at this very early on. It's just like, what the heck is that? And so think of this like a vector sum. This is like, you can think of it as cosine phi times the x unit vector, the real unit vector, plus sine of phi, that's this length right here, times the y unit vector. And so it's just sort of a vector sum, like this plus this, and then you get that length 1 vector. Now, what about, we have to talk a little bit about the way sine and cosine are different from each other. So what about like the negative 1? So if we look at the negative 1, you can see that the imaginary part changes, but the real part's the same. And that's because sine and cosine are kind of different from each other. One is symmetrical around 0, and the other one isn't. And so I think it's worth writing this out. So you often see e to the minus I like when I first wrote up the Fourier transform. And so we can think of that as, e to the I minus phi, but then what does that equal? So that equals the cosine of, minus phi plus I times the sine of minus phi. But what does that equal? Well, it turns out the cosine of minus phi is the same as the cosine of phi, or phi. So, because that r, the adjacent, if we take a negative angle here, the adjacent side doesn't change. The adjacent side of the right triangle doesn't change, but the opposite side, which is the sine, does change. It goes from I to minus I. So that means that that's the same as cosine of phi. Cosine of minus phi is the same as, cosine of phi. And then we can take this minus. So the sine of minus phi is the same as minus sine of phi. So we can just take this guy out here. And so you'll often see it written out this way. But that I just sort of very slowly went through the whole transformation. So what is that? That's what e to the minus I looks like. So you subtract off the sine, go down, subtract off the sine, but the cosine doesn't change. So you can see it all sort of fits together in a strange way. So what about this? Why, when we change to cosine of minus an angle, is it the same? Well, if you just look at the cosine graph, you can see. So here's a cosine graph. It looks like this. I'm partly negative there, so there's 0. That would be 1. So if you go out a certain distance in a positive direction, you'll get the same number as the distance in the negative direction. So we call that one an even function. It's not. There's many other even functions, but it's symmetrical around the. So no matter where you go, it's always exactly the same if you take the negative argument. But the sine is different. So sine looks like this. So now if we go out a certain distance in the x direction, and then compare what happens if we go out the same distance in the y direction, we get the negative. Those are the same number. This is just the negative of this one. So that's an odd function. And because of that, you get this sort of asymmetry here when you change the negative. When you change to a negative angle, it doesn't change the cosine, but it does change the sine. Okay, so that was. This is slightly strange when you first see it. Like, where's that negative coming from? And why isn't it on the cosine? It is on the cosine. It's just that it turns out the cosine is the same whether it's the argument is negative or positive. Okay, so the good thing about decomposing something like an image into cosines and sines is that they're all uncorrelated with each other. And so what does that mean? So that means like the correlations. And what does correlation mean? Again, correlation just means you get a bunch of pairs of things and multiply them by each other, add it all up, and the answer is the correlation. If it's 0, it means they're uncorrelated. If it's positive, it means they're positively correlated. If it's negative, it means they're negatively correlated. So So basically, if you take the correlation of the cosine of some frequency times, as a function of time. So this guy, just say, for example, 3 or something like that in our example from last time. So if you take the correlation between that and the sine of that same frequency, it's 0. So, for example, there's a 3 in there too. So that's what I was saying last time, that if you imagine you've got a cosine here and a sine like this, that's just going over 360 degrees. There we go, get it back to the right place. What does correlation mean? Correlation means, like, think of the cosine as just a long vector. Each of these numbers are like numbers in the vector. Think of it as a 1,000-dimensional vector, or an infinite number of points. And then think of the sine as another vector, which consists of all these numbers. Those are all the coordinates of that other vector. Multiply them all times each other, add them up, and you get 0. I didn't draw the sign very good, but you can just try it. It's sort of a magical thing. Like, they all just cancel out. All those numbers multiplied by each other cancel out. And so so cosine is completely uncorrelated with sine. But it turns out that other frequencies are that way too. So if you correlate, one frequency with another one, say just take cosine, of frequency, 1 correlated with also a cosine of frequency 2. That also equals 0. So what would this be? This would be like, say that one was frequency 1, and say this one was frequency 2. So it turns out those are also completely uncorrelated with each other. And so that would, if we just look at 0 to 360 worth of it, so we have a cosine of, so there's a cosine of 1, and then what's a cosine of 2 look like? It looks like it goes, like that. So those turn out to, and so if you multiply all those guys times each other, they're also completely uncorrelated. And so all the different frequencies are uncorrelated with each other, and sine and cosine are uncorrelated with each other. When you first hear about this, it's kind of weird. Like, why do we need like sine and cosine? What about just all the different frequencies? Wouldn't that be enough? But it's not enough. So you need sort of like all the different frequencies plus sine and cosine at all those different frequencies to completely sort of describe another function in the other domain. Okay, so once again, that's going to be 0. And if in the infinite limit of like infinitely fine number of points, any frequency, even, here we were just comparing like frequency 1 to frequency 2, but if you extend out infinitely, frequency 1 is completely uncorrelated with frequency 1.00001 if you extend it out over a large distance. Okay, so that was, our orthogonal decomposition and how to sort of think about it just with a straightforward XY coordinate system here, where the imaginary part is the y-axis. So what we want to do now is change over to space. So we already said this a couple times, but this is, when you first hear about it, it's kind of a little bit of a confusing thing, because what does spatial frequency mean? It just means some kind of sinusoidal variation in brightness across space. So there's no time involved anymore. It's just change in brightness that is a nice uniform sinusoid, like a cosine or a sine, with varying numbers of bumps, depending on how many you're currently considering, going across the image in a particular direction. So that's the meaning of spatial frequency. So if we write out the 1D Fourier transform that we had before, here's the Fourier transform result, and that equals the sum across all time of the value of a function at a particular point in time times this e to the minus I 2 pi times f times time for every point in time. So that was our Fourier transform. And what does this thing turn out to be? It's just basically sine and cosine. It's two-dimensional thing, sine and cosine. And so we correlate with a sine and a cosine, correlate this thing with a sine and a cosine across all time. And then we get, for a particular f, we get one frequency. So that was, we can do it in more than one dimension, and that's what we're going to extend to. But this is just a one-dimensional Fourier transform. You can write it out with two dimensions, but don't get confused. So you got sort of two dimensions of cosine and sine, or real and imaginary, but you also have separately two dimensions of space. So it's easy to sort of like get confused. Make sure you allocate enough memory for all the different parts. So when we transition to thinking about spatial frequency, we usually use k instead of f. So that's why it's k-space. So k is the spatial frequency variable. And what are we doing? We're summing for a one-dimensional Fourier transform. We're summing across all space instead of time. So here's that function. Now it's a function of x. So it's a function that has a certain brightness in the image at a particular x coordinate. That's the meaning of that guy. And then we'll be multiplying by this mess again, 2 pi. But instead of f, we use k, and instead of t, we have x. And then we're summing across all x. So that's exactly the same equation. All we did was just change the letters. So basically frequency goes to k, which is spatial frequency. Time, goes to x, and then, there's time going to x, and, frequency goes to k for one spatial frequency. So, so we have, so basically we can go back and forth between temporal frequency on the left here. So this equation tells you how to go from time to temporal frequency, the top one. But the second one tells you how to go from space to spatial frequency. So this is the Fourier, so that's the forward Fourier transform going that way. And then that's the inverse Fourier transform, which we said is exactly the same, except just take out the minus. So that's the inverse. And the second equation was spatial frequency. When we Fourier transform, sorry, I got my arrows wrong here. So when we go from, so this equation, when we go this way from temporal frequency to this side of the equation, is basically, it depends on how you think about it. Do you think about sort of space being on the left and then the more strange marked thing, spatial frequency, being on the right, or the way we're doing it here, which is the strange thing, which is spatial frequency on the left of the equation and space on the right of the equation. So when we go back and forth between, we can use the Fourier transform to sort of go back and forth between space and time. And what this equation here says is, here's how you Fourier transform this guy into that guy. And the inverse Fourier transform is taking this guy and getting back to that guy. So that's our sort of changing from time to space. So let's now, without doing the equations, just extend to 2 dimensions of space. So there's multiple things to keep in mind. We got real and imaginary, but then we also have 2 dimensions of space. So the way I always pitch this is you've got to allocate memory for all these different kinds of things. Don't get them confused. So you start off with sort of a general idea about the Fourier transform, and then we slowly have to sort of like, make a bunch of cubicles to store all these different things. And so we'll make 10 cubicles. So 10 different ways of looking at space and spatial frequency. So if we start off now I'm going to sort of flip it. So here we had sort of spatial frequency on the left and space on the right. So now we're going to flip and put space on the left and spatial frequency on the right. That's almost sort of more natural because you think of space as kind of a thing you can understand, and the spatial frequency is some weird thing. So if we have an image here, so this side of the, we'll put a dividing line there. So we got an image here, so that's space. And there's basically 5 different ways we can sort of think of representing that image. And so here's the image. Say it's like a brain. So there's a brain. So what is this? This is the real value. Remember, these functions all have to be complex valued functions. So that's the real value. And what is the imaginary value of the image? Well, it's all 0. But we're forced to insert a complex number in for our Fourier transform. So that's our imaginary part. That's the imaginary part of the image, which is all 0. And what are the dimensions here? So the dimensions here are not sort of real and imaginary. The dimensions are x and y. So that's x, and that's y. So it's a two-dimensional image. We could have a one-dimensional image. That would just be like something like that. That's a one-dimensional image. That's the brightness of the image, and this is x going across the image. But this is a two-dimensional image. So we have x and y. But then in addition, we've got real and imaginary, which are sort of like x and y also. Now we could also look at that. We can convert that to polar coordinates, which is commonly the way that you look at this. And how do you do that? You take the real part and the imaginary part, and you convert that into this angle and amplitude. So if we do that, that's another way of looking at an image in polar coordinates of real and imaginary. But instead of real and imaginary, you end up with amplitude and phase. At first, when you first see this, you go like, we just got an image. Why do you have to mess it up with this other thing? But you'll see that when we eventually do a reconstruction, we end up with a complex valued image, and the phase turns out to not all be 0. That's why we usually throw it out and look at the amplitude image. So we can convert this image into amplitude and phase. So now we've got amplitude over here. That's the A. And here's the phase. That's the phi. And so what does that look like? It's looks exactly the same. So the amplitude, if we imagine we've got an all positive image, all positive numbers, what is the, remember, if this is a real image, it doesn't have any imaginary parts, then the angle of phi is always going to be 0. And so this will be 0 again. So the amplitude will look exactly the same as the real. Now, what to me is like the most intuitive way of looking at it, just think of the little complex vectors. So if you think of those complex 2D vectors, like it was over here, but like the like when you had the, like here's a vector like that, and it's got a real and imaginary part. Why don't we just draw the little vectors like little things into the image? And so here's the image, and what will it look like? It will look like a bunch of little vectors. They'll all be pointing in the right direction with a phase angle of 0 degrees, because it's 0 over here. So they'll all be along the positive x-axis. And some of them will be bigger. The brighter parts will be bigger, and the dimmer parts, like say the gray matter, will be slightly smaller, but they'll all be pointing in the same direction. A lot of little vectors. And there'll be little tiny vectors out here too, out in the black around the brain. So, but they'll be sort of tiny vect. So that's kind of the way you should think of an image. Yeah. So it's a bunch of little vectors that could potentially have some other phase, image phase. So that's the problem. We're just kind of embedding this complex valued xy coordinate system in another xy coordinate system. That's the part that can be difficult to make sure you got it separated in your mind. Okay, so this is all the image side. So now we go to the spatial frequency side. So this is where it gets weirder. So here's the spatial frequency side, and how do we get there? We get over there by doing a Fourier transform, and we get back by doing the inverse Fourier transform. So what does that look like? So that has the same number. So here's 5 different ways of looking at at an image, at a real image, real valued image. So now what we want to do is 5 different ways of looking at the Fourier transform of a real image. So you got 10. You have to allocate space for 10 different kinds of representations. This is a very concrete thing. This is what you do when we do the Fourier transform homework. You'll like say, take an image. Show me this. You don't have to do this. This is a little more fiddly because you'd have to draw out a little bunch of arrows. But then take the Fourier transform of it. Show me the real and the imaginary part of the Fourier transform. Show me the amplitude and the phase of the Fourier transform. Those are all MATLAB functions, just one-line MATLAB functions. But it's important to sort of allocate mental space for them before we start using the MATLAB. So we end up with 2 representations here. And what are these representations? It's real spatial frequency and imaginary spatial frequency. And that sort of seems kind of unhelpful and abstract, but let's just try to make it very concrete. So the way this is usually written out is, if you look at these equations here, you can easily put in a negative for frequency. So you could put in like 2 here for like 2 bumps every time you go around 360 degrees, but you could also put in -2. So negative frequencies are perfectly okay too. You can run the equation with f being negative. And so the very center of this is 0 spatial frequency. And we'll talk on Friday, what does that mean? That's a really important, it's like the most important spot in the entire k-space. So this is, this is k-space here. which means just spatial frequency space. So spatial frequency 0 is in the middle, and then spatial frequency 1 is like, just off to the right. And so what is this, if we look at this, what does it look like? Well, it's got like a whole bunch of stuff in the middle. It's a bunch of big numbers in the middle. And then as you go off to the side, the numbers are much smaller. It's a big spike in the middle. Like if you took the Fourier transforms, spatial 2D Fourier transform of the brain, both in the real and the imaginary case, the big numbers would all be in the middle, like that. And so first of all, what are the coordinates here? So the coordinates here are the x spatial frequency, and then the y spatial frequency. So that's the actual sort of coordinates here. So what does that mean? Or, let's first of all say, why does the brain have low spatial frequencies in it? Why is spatial frequency 1, 2, 3, and 4 really prominent in the brain, and spatial frequency 127 is very small? So it turns out if you just look out into the world at objects in the world like chairs, people sitting at the desks, low spatial frequencies predominate. If I look at the carpet, so if I just screened out everything and looked at the carpet, now we have high spatial frequencies, because there might be like 127 or 275 little bright and dark spots in the carpet as I look across the carpet. But carpets are kind of strange things, and so if you look out in the world at like a tree or a cat or a leaf or something like that, that's really dominated by low spatial frequencies. And so typical natural images that aren't of things like carpets are going to have mostly low spatial frequencies. And so that's the explanation for why you got this big peak in the middle of spatial frequencies. So the one example I always point out, like with a brain image like that, what's the most prominent spatial frequency in this brain? So let's draw a line across this brain. And what is that? Just do it in 1D. What does that look like? Well, it's kind of dark, and then the brain starts, and then there's some variations in different parts of the brain, and then it gets dark again. So what is the biggest spatial frequency in that? By far the biggest spatial frequency. Like 5, 3, 27, any guesses? 1 is by far the biggest spatial frequency. And why is that? Well, let's take a cosine. So what does a cosine look? A cosine looks like this. That's a cosine. That's a cosine of 1 times 1 times x. So x is the variable. So this x is the variable here. So if you take a cosine of 1x, that's frequency equals k equals 1. Okay, so if you take a cosine of 1x, it's really correlated with that. It's negatively correlated with it, right? So it looks like an upside down cosine. So there's going to be a 180 degree phase. Like if you move that cosine off to the side, half of the width of the image, it would correlate really well with it, right? So you just imagine we take this guy and sort of move him over about halfway. What would happen is you'd end up with something that looks like that. And that correlates, if we now multiply that image times that guy, they're really correlated with each other because those numbers are all very similar to each other. And so if we, so that's the highest spatial frequency that you have, spatial frequency 1. because what does it look like? Dark, light, dark. That looks like a cosine of 1. Now there's other spatial frequencies. There's little bumps, like you got gray matter, and you got little, the gray matter varies a little bit, but it's nothing like, black, a lot of high contrast image, and then black again. So that's how we're thinking about the data as spatial frequencies. Now, you might wonder, well, what's the kx and ky business? So if we go over here, that would be like, kx, say, equals 5, ky equals 0. What does that mean? That means 5 vertical stripes. That's what kx equals 5 means. So it would be 5 vertical stripes, if we think of, what it represents back in image space. What about if we went like over here? So if we went over here, say we went to, kx equals 5, ky equals 5. In that case, we're going to have 45-degree angle stripes. That's going to correspond to 45-degree angle stripes here when we have both x and y spatial frequency. If we went on the right along the y-axis, the ky axis, then we would have horizontal stripes, 5 horizontal stripes. That's what this number would be. So this number would be, horizontal stripes back there. This one would be vertical stripes there, and then this guy would be 45-degree stripes back there. So that's what this. So you're going to get thousands of numbers that represent the stripe amount in our image back there. That's what a Fourier transform of an image means. It contains all the information that the image has. So you can, when you inverse Fourier transform that, you get all the way back to the image, you get all the different parts of the image. Okay, so that was our real spatial frequency and imaginary spatial frequency, but we can look at it in a different way with amplitude and phase, which is more commonly how you look at it. So if you do, that conversion where you change, real and imaginary into polar coordinates, what do you get out? You get out, for the amplitude case, a whole bunch of very large numbers at the middle, just like before. But for the phase case, it looks now just like numbers that go between, minus pi and pi, minus 180 to plus 180, or 0 to 360, either way, same thing. And so they're just all over the place. They're no longer concentrated in the middle because they just represent the offset for each of these stripe patterns. So each of the stripe patterns, after you correlate with the sine and a cosine, will tell you like what is the best offset sinusoid that fits. And so these are all the offsets. So this is the amplitude picture of spatial frequency. And that's usually when you think of a Fourier transform of an image, what you're thinking of. And then this is the phase of the spatial frequency. And finally, last but not least, we could sort of think of it as vectors. And so if we think of it as vectors, what is it going to look like? Well, there'll be some vectors pointing, some big vectors, relatively big in the middle, where that spike is, pointing in various directions, different phases. And then as you go off, there'll be two little teeny tiny ones, tiny vect, out in the periphery. The big vectors will be all in the middle because that's where the amplitude, that's where the spatial frequency 1 is, because that's the biggest spatial frequency. Okay, so We got Fourier lands, frequency land over here, not frequency land over here. And we've got 10 different ways of sort of looking at these two. So you can either think of it as real and imaginary, or we can think of it as polar coordinates, amplitude and phase. Or we could just think of it as a bunch of little arrows that sort of contain both amplitude and phase. Or we could Fourier transform them and end up with the same thing over here, same number of numbers. So we'll have, real spatial frequency, imaginary spatial frequency, or amplitude of spatial frequency, or phase of spatial frequency, or vectors of spatial frequency. Okay, so that's so we've allocated 10 two-dimensional memory locations to keep in mind. Don't get confused. And so for the last bit, let's just power through without equations a concrete example of a very simple kind of a brain, which we'll call the cosine brain. It just happens that your brain, it does actually look quite a bit like a cosine. So let's just actually go through and write up these two views of, so there'll be 20 little squares I'm putting up because I'm going to do it twice. Once where we're tweaking the phase to sort of show you what the phase, concretely means. Okay, so start off with a real-only image. So let's divide the board so I don't screw up halfway through. Okay, so we're going to do a real image with the phase tweaked. So just a real-only image. Why am I saying that? Well, when we get to gradients, we'll see that gradients are not, what gradients do to the brain is not real only. So that's on Friday, but we'll start off with a real only image. And so what is our image equation? So our image brightness at point xy is just equal to the cosine of x. So notice y isn't in there. And so that means it doesn't matter what y is, it's always the same. The image brightness is always the same. And if you go in the x direction, the image brightness changes. And so what does that look like? What do those 10 representations that I had last time look like? I'll fit them all into here. So first we could do real and imaginary. So here's real and imaginary. So in the notes, since the notes are on white paper, I've drawn the cosine brain out. Imagine that this bright thing I'm drawing here is actually dark. I'll draw it the same as it is in the notes, so it's less confusing. So basically what you have is just a sinusoidal variation in brightness going across. So if I just plot that out, what does it look like? It's just a cosine. So it's just a cosine of, you could sort of think of this as a cosine of, 1 times x, frequency 1. K equals 1, times x. So it's just a cosine. You go across this direction. In this direction, it's constant. And so what's going on over here? It's all 0 over here because it's a real only image. So now it gets a little bit slightly hairy. So this is, real over here, and then imaginary on the image side before we've done the Fourier transform. But we could also think of this in terms of polar coordinates of the complex numbers. Here it's a little funky. So what happens when we look at the amplitude of that, the amplitude of this, and remember the amplitude of this is basically, how do we get the amplitude of a complex number? We just take the real squared plus the imaginary squared, take the square root of that. That's how we calculate the amplitude. But since the imaginary part is 0, it's basically just the real part squared, square root, so it's just the real part. So the amplitude will just be the same as the real part, but all positive. And so if you do this in MATLAB, you'll get something that looks like, the amplitude, but then it's positive again. The negative part of it is positive, like that, and then it'll be positive again. So what will that look like if you plotted that out in MATLAB? Well, you would get like a dark thing over here. You get two little dark things. It's a little confusing, but sort of all makes sense because we're just measuring the positive only amplitude of that. So this is the amplitude of our cosine, which is the same as the cosine after sort of taking the absolute value. And then here's the phase. And the phase is going to be a little funky too, because when we take the phase, what's going to happen is we've got some, we've got to deal with that negative part there. So what will happen is you'll have something that looks like this. The phase will be in the middle. The phase is going to be, 180, pointing to the left. 180, and it'll be 0 degrees here. So that's kind of strange. You could also think of it finally as arrows. So how would you think of it as arrows? Well, it's going to be the largest arrows right in the middle, pointing in the negative direction, like that. And then whereas the largest positive arrows are going to be on the ends here, pointing in the positive x direction, and also over here, because the cosine wraps around. So there's the arrows. They're all along the x-axis, and then as you go, then there'll be smaller arrows here, etc., and smaller arrows here, and then when you get down to here, there'll be 0 length arrows. So this is slightly smaller ones like that. Okay, so you get the idea. I won't draw them all in. So that's our picture of, on the notes they're all drawn in. So that's our picture of the vectors. So now, Fourier transform this thing. And so what do we do when we Fourier transform it? We end up with 10 more things. So let me draw them all here first. There's 10 more ways of looking at, 5 more ways of looking at this. So we could look at it as either real and imaginary spatial frequency, or amplitude and phase of spatial frequency, or just the vectors of spatial frequency. So what does it look like here? So the first strange thing is that there's 2 spots over here. So there'll be 0 again over here, all 0 for the imaginary, and there'll be all 0 for the phase. But there'll be 2 spots here, and they'll both be at, they'll be at 1 and -1, because this is spatial frequency 1. Now, why are there 2? That's kind of like a strange thing. And if you come to the Friday session, we can sort of go over how you can think of what's going on here with correlations with these little spikes. But you need, to specify a cosine, you need 2 numbers. You need a +1 spatial frequency and also -1 spatial frequency. So if you convert that to amplitude and phase, you get the same thing. You get 2 spots right at spatial frequency 1. And if you convert that to vectors, you get two little vectors, and they're both pointing in the positive x direction, the positive kx direction. So that's our Fourier transform of a cosine brane. It's just got two spots in k-space, +1, -1 spatial frequency right along the x-axis because it's a vertical stripe. If we used a horizontal stripe, it would be along the y-axis, the ky axis. So remember, this is, ky, and this is kx, and this is, x and y. Okay, so that's our Fourier transform of a cosine brane. It just has one frequency in it, one x spatial frequency, so there's no y spatial frequency, it's just one x spatial frequency, but it's got this complicated thing where you got like two of them, and we'll come back to that. So a cosine corresponds to two spots in k-space. So this is our Fourier transform of real image. So now let's do the same thing. So we need 10 more squares. So 10 more squares here. And we'll just do one little tweak, which is just to offset our brane a little bit. So here's a real only image, and here's ft of it. So what's our equation here? So our equation is just the image brightness at an xy point doesn't depend on y at all, it just depends on x. And the only thing that we've done is we just offset the cosine a little bit. And so how do we offset it? We just subtract an angle off it. And so we'll subtract off pi over 4. So what is that? That's just 45 degrees. Pi over 4 is 45 degrees. So basically, if we subtract off an angle, that will move it to the right. So convince yourself in MATLAB that's what happens if you subtract something off the argument of cosine. Subtracting moves it to the right. Adding moves it to the left. So what does it look like now? Well, it just moved the stripe a little bit over to the left. So it used to be here, so it just moved it over. It moved it over just a little bit to the left. So our cosine stripe's just going to be a little bit to the left like that. So it looks the same as before. We just shifted it. Still all 0 here. And so just label everything. So here's real, imaginary, but now we're in spatial frequency land because, we did ft to get this way. So we got real and imaginary, and we also got amplitude and phase of spatial frequency. And, of real image still. And here's amplitude and phase. Man, doesn't go here. Goes here. Okay. That goes here. Okay, so we got real imaginary amplitude and phase, and then vectors down here. And here again we have real and imaginary, amplitude, phase, vectors again. Okay, got everything straightened up. So the only difference is we moved the cosine off to the side by just subtracting a little bit to it from it. And so what happens when we look at our picture over here, well, it's going to move these two little stripes off to the side a little bit. Sorry, let me get rid of those things out of there. I didn't mean to put those in there. So our two little funky stripes are going to be moved off to the side. Our, phase picture is going to move off to the side. And our arrows are going to be moved off to the side. So the maximum left arrow, the maximum negative left arrow. So what is it? I should draw it over here. So what does it look like? So here's what we had before. That was a cosine. So what do we have now? All we've done is just shifted it over to the right a little bit. So it just looks like this. Something like that. All we did is we just shifted that guy to the right. And so our maximum arrows are going to be shifted off to the maximum negative arrows are going to be shifted off to the right. The maximum positive arrows are going to be, shifted off to the right. So it'll be something, like that, etc. So what does that do when we Fourier transform it? So when you Fourier transform it, we haven't changed the spatial frequency. And so we'll still have 0 over here for the imaginary parts, and we'll just have spatial frequency 1 because it's still just a cosine. It's still just a cosine. What about amplitude and phase? Amplitude and phase is now going, so the amplitude is still just going to be at spatial frequency 1 and spatial frequency -1. So here's spatial frequency 1, that's kx equals 1, ky equals 0. And then this guy is kx equals -1, ky equals 0. So that's going to be the same. But now what's going to happen is, we're also going to have an imaginary part. And that's a little harder to think about than just thinking about the amplitude and phase part. What's going to happen now is we're going to have a positive phase here and a negative phase there. So this is, kx of the phase is positive, and this guy, k. So at kx, at kx equals 1, the phase is positive. At kx equals -1, the phase equals negative. So how does that look if we make out little arrows? We get a sort of an arrow pointing up over here and an arrow pointing down over there at 45 degrees. And that's the same 45 degrees as we have here. So this just goes back to talking about offsets. So what does the phase of the Fourier transform represent? It basically just represents, for each frequency, where is it placed? Where is that ripple in brightness placed? Is it placed like just a bare cosine, in which case the phase would be 0, so the phase would be along the x, just positive x-axis? Or is it a little offset? And when it's offset, what does that do? That moves the image. So the phase will tell you essentially where, if you mess with the phase, it'll actually move the image. It won't change the shape of the image. It will just kind of wrap the image around and move the cosine. What does messing with the phase do? It just took that cosine and just moved it over. And when we talk about all different kinds of artifacts in imaging, you'll see stuff like this where stuff gets moved around. And we'll go over the equations for this to sort of straighten it out, but I thought it was better to just start without equations. So you have a cosine brane. You can think of it either as real, imaginary, amplitude, and phase, or arrows. And then we Fourier transform it. And when we do that, we get just two spots in k-space. Spatial frequency 1 and spatial frequency -1. And we can think of that as just two little vectors with 0 phase, because phase is 0, so that means they're along the x-axis. We just take a cosine brane again, do nothing but just shift it off to the right by subtracting 45 degrees from it. And so you can look at that as real or imaginary. It's a shifted cosine, or amplitude and phase, or as vectors. Now the vectors are shifted. And then when we Fourier transform that, we get two spots in k-space, but now there's a real and an imaginary part because the phase isn't 0. And so when we convert to amplitude and phase, instead of getting 0 for the phase, we get a positive number for the positive spatial frequency coordinate and a negative number for the negative spatial frequency coordinate. It's a particular kind of symmetry of the Fourier transform that we'll talk about on Friday. And we could draw that out as these little vectors. You got like a positive phase on this one and a negative phase on that one. And what is the result of doing that? It's just to shift the image, because that's what the Fourier transform is about. It decomposes things into sinusoidal variations in brightness, and it tells you how much of that variation is there. That's the amplitude. And then the phase tells you what is the offset of that variation. Now, I just did it for spatial frequency 1 here, but the same thing applies to spatial frequency 2 and spatial frequency 127. They all have their phases. Their phases are all different. Okay, so we powered through. How is it's going okay? Fourier transform day 2. Any questions? I'm already 12 minutes over, but any for the diehards? Any questions at the last second? You're starting to allocate all these. Got to allocate 10 XY plots, brain space for 10 XY plots. Okay, so we'll go over the equations, the actual equations for this. They're not very hard. They're just like Fourier transform with one extra thing in it. Okay. See if I made any screwed up on anything. Everything looks okay.